Alright, folks. There seems to be some kind of audio issue in this particular track at this time, and so we don't have any audio in this video until about the 7 minute, 30-second mark. Sorry for the inconvenience.
And in my opinion, at least for real-time capture, when we're talking about an agent-based solution, the only tenable solution is to call it with the custom event handler. So let's look at a couple of solutions for real-time ETW, starting with Win32 Event Tracing API. It's cumbersome and inflexible, written in 1892, programmed like it's 1992. And unfortunately, it's just not, it's rough. If you've ever written Win32, you'll know what I mean. There's, in the base class libraries of .NET, there's actually system.diagnostics.eventing. But we found it to be unreliable, and the performance is not very good CPU and memory-wise. We've had problems with it parsing data incorrectly, not very well. So that wasn't a very tenable solution with a number of providers enabled. Finally, there's trace event. And I say it has poor performance here. It's poor performance on the memory side. When you turn on lots of providers, you have a problem with, okay, you've made all these managed objects, and it's one for every event. So imagine a managed object for every packet event. That's a lot of objects, and you're going to have to garbage collect them all aggressively. Instead, we could talk about krabsetw, which is the library my team open sourced last fall. It's available already today if you wanted to look it up. It was built specifically for managed and native. It has a modern C++ API. The managed interface is written in C++ CLI, so it works with .NET, PowerShell, all sorts of things like that. It's meant to be flexible and intuitive, and we'll get to some examples that will show that better. We built it for performance and reliability. It's built for Office 365 scale, and it's compatible all the way down to Windows 7, Windows 2008 R2, because we have a couple of teams that we still support for that. Excuse me. All right, we're going to do some examples. I'm not live coding. I'm not that brave. We'll look at some example detections, and these are simplified versions that come from our own agent in production. And they're on GitHub. I'll have a link for those at the end for people. And I hope that this is illustrative of how you can use these in your environment. If it's not, then please come talk to me. So let's start with DNS. Something we wanted to know was, what's every single DNS lookup that's happening in the environment or on a computer? What's it looking up? And so here, this is code for doing this. Up there at number 1, we've built an event filter. We're looking for event ID 3018 and event ID 3020. As you can see from the comments, 3018 is cache lookup, 3020 is live lookup. Then we're setting up an on-event handler, takes an event record object. And we're going to parse out a property named query name. It's represented by a Unicode string. And that's the domain that you looked up, say fubar.com, newyorktimes.com, etc. And then the next one, that next line, result equals get Unicode string, that's going to be the query result. So whether it's the A record or the quadruple A record or the MX record, etc. And then we're just going to print it out. At number 3, that's our provider object. And that provider object is it's not the provider itself, it represents the registration for a provider. And so in this case, the provider is called Microsoft Windows DNS Client. And then we're going to add that filter we built in 1 and 2 to the provider object. And number 4 is easy. This is just creating the trace session. Then we're going to enable our provider on the trace session. And then we're going to set up a event handler so that we can handle calling trace.stop properly. And then we call start. Now, unfortunately, with this example, one thing to note is that this will not catch chrome.exe. Chrome uses their own DNS resolver. This is only focused on the resolver that's in Windows built into WinINet. Here's our example output. Excuse me. You can see responses from things like Cloudflare and Optimizely and Google Analytics. Where you see type 5, those are CNAME records coming back. You see some A records, some quadruple A records, etc. in there. And right now, I'm not aware of any other way to do this in the operating system. So if you know of a way besides scraping the WinINet cache, please tell me. This is in real time as it happens. So let's look at, what if a process loaded PowerShell? Typically, we see PowerShell.exe and WSM host are the only two processes that are loading PowerShell. Maybe a couple of others in your environment, depending on what they're doing. But it's not very common in our experience. They're rare, or the exceptions are rare, so your mileage may vary. Number one, again, we're going to look for event ID 5. That is, in this case, image load, which is another name for a DLL load. And we're going to look for a Unicode string for the property image name where it ends with system.management.automation.dll. Then in number 2, we're going to set up the event handler again. We're going to pull the process ID out for the process that did this. We're going to pull out the process name just using process.getProcessById. And then we're going to pull out the image name itself, which is actually kind of redundant given our filter, but it's in there. And then we're going to print out what's happened. But actually, the image name will give us the full path, so if for some reason they're loading a particularly special system.management.automation, you'll see that too. Number 3, same as our previous example. We are, except this time we will be listening to Microsoft Windows kernel process. That's another user mode provider, despite the fact that it says kernel. Then we're going to set up our trace again. Set up the provider on the trace, enable Control-C for stopping the trace, and then call trace.start. So here's an example of the output. On the bottom in the black is output from the example code that I wrote. And on the top terminal is psattack.exe. Now, if you look at the highlighted portions in the black terminal, you'll notice that it says psattack and then PID 1584. And if you look up top, you'll see that that says psattack 1584. PID 1584. You can use this technique this will catch any instance of someone loading PowerShell DLL. It doesn't matter if it's not PowerShell.exe. It doesn't matter if it's your red team's custom malware. It doesn't matter. None of that matters. If it gets loaded, it's going to run. And excuse me. So you can imagine building other detections, like say winlogon.exe loads.net. That might be weird. And that's speculation on my part. I'm not saying that's actually a valid detection. Let's look at PowerShell method execution. See what sorts of PowerShell methods are executing in your various contexts. Event ID 7937, that's from the PowerShell trace. We're going to look for payload started because we don't care about the stop events. We just want to know each individual method that started. Set up our event handler. We're going to pull out that context info block I talked about earlier, which has that big, well-formatted string of properties. And then we're just going to print it out. And again, provider, Microsoft Windows PowerShell. Number 4, nothing new here, same exact pattern. Here's our example. Bottom terminal, again, is the example code. Top terminal is psattack. So I wrote a little file, foo.ps1, that has invoke mimikatz in it, just a fake one for giggles. And I start psattack, and then I run the script. Well, on the bottom there, you can see at the top that we've highlighted the host name is psattack. The host application is the path to psattack. The command name is invoke mimikatz. And the script name, even, for where the script came from, is foo.ps1 in my folder. And then, of course, the user that I talked about earlier. There might be more useful information in there that could be correlated, and you can harass Lee about that. I'm not actually sure. And then, now let's look at thread injection. So, excuse me. For this example, we'll look at thread creations, and thread creation is kind of a tricky business. Number 1 there, we're going to look for event ID 3, which is the thread create event. At number 2, we're going to pull out the source PID, which is the PID that is associated with the event that generated it. Then we're going to pull out the target PID, which is the target PID for the property process ID. That actually points at the process where the thread was injected. So if it created a thread in its own process, that would be the same as the source PID. Oops, sorry. And then we're going to look if source PID is not the same as the target PID. And that's a very basic filter at the beginning. We also have another check we could do, but I left it out for brevity. And it's to check if the parent process is the same as the source process. Because if that's the case, it's possible that this is the initial thread creation. The way Windows works, when it creates a new process is it actually creates a new thread object first, and then it creates a process object that wraps the initial thread. And so when you're looking at this in ETW, you actually see the thread create happen before you see the process create happen. Excuse me. Then we're going to pull out the thread ID, print it out. 3 is the same as before. 4 is the same as before. Nothing new here. Main thing with 3 is that we're using Microsoft Windows kernel process like we used for the image load detection. Here's our sample output. So the highlighted lines are the ones that I think are interesting. I left in source PID 4 to some target PID because that's actually quite common. The system process frequently injects threads into other things. It's kind of gross, but it's just the way Windows works. Something to note with this particular detection is that it's a heuristic. Remote thread injections actually happen for legitimate reasons regularly in the operating system, and 2 big ones that you'll see are COM and performance counters. Let's go back to our forensic wish list. What DNS lookups did it perform? We talked about that in an example, Microsoft Windows DNS client. What IP addresses did it connect to? How much data was transmitted? Is it beaconing? You can get all of that from Microsoft Windows kernel network. What DLLs did it load? Did it create threads in any other processes? You can get that from Microsoft Windows kernel process. We talked about that. What WMI operations did it perform? Microsoft-Windows-WMI. What PowerShell functions were called? Microsoft Windows PowerShell. Keep in mind that I've given you ingredients. I've not given you recipes when I talk about these sources. And so the detections are meant to show you the really, really basic recipe, right? Making bread is flour and water. But making really, really good croissants is also adding some other things. So let's go back to bad.exe and let's see a hypothetical scenario of what you might have seen having ETW as a detection capability. And we'll revisit some of those detections we just talked about, and I'll give a couple little more notes there. And it has lots of information in each of these slides. I mostly put that in there for people to have for reading later, but I will be not speaking to all the points. So here's our original process start. There's no new detection here. Perhaps the initial detection was looking for process starts in System32 with an uncommon binary. PowerShell DLL loaded. So with a PowerShell DLL loaded detection, we saw that bad.exe loaded system.automation.dll. Again, looking for the DLL load of system.management.automation. It's a heuristic detection. It doesn't always indicate bad, but it's really, really good at giving you high fidelity signals in general. Then we get to obfuscated PowerShell. After loading the PowerShell runtime, it's only logical that bad.exe executes in PowerShell. In this case, we saw bad.exe execute some gibberish-looking method names, like ASDF1234. We can use a couple of statistical methods to identify strings that look like gibberish or non-English strings. And 2 examples of that are Shannon entropy and bigram analysis. Shannon entropy will tell you how random a string looks like, and bigram analysis tells you how English-looking a word might be. Well, actually, bigram analysis can be generalized to other languages as well. It just happens that English is what we're using here. So this is also similar to the malicious PowerShell example I showed before. Actually, the PowerShell method execution example I showed before. We're just pulling out these method names and throwing them through some sort of word scorer. And something to note here is some of y'all may have watched Daniel Bohannon's talks on invoke obfuscation. He talks about clever ways to obfuscate calls to things like invoke expression, using strange escaping, or recombining strings together. That sort of obfuscation doesn't work here. At the point at which we get the log for the invoke expression call, we actually already have symbol resolution done in PowerShell's parser. So you will still see invoke expression. So the obfuscation will help in script block logging, but it will not help in trying to avoid this detection. DNS lookups. After calling the strange obfuscated function name, we saw a suspicious DNS lookup. Maybe it was machine superserver querying for fanciestbear.com and going to, that returns back IP 1.2.3.4. We talked about it earlier a little bit, But I alluded to it, but I didn't actually speak to this point. One problem you'll have is you won't be able to tie process from the event to who did the DNS lookup. And that's because WinINet is actually serviced from servicehost.exe whenever you resolve a DNS resolution. And so it always looks like it's coming from the service host process. So the way you do that is you actually need to track per process, per IP endpoint, what addresses they've talked to. And then when you track your DNS resolutions, you'll have to track a reverse table of domain name to IP address. And then the way we do it was we actually periodically log the data that's sent out and reassociate up domain names to IP addresses. You can also do it when process exits, for example, although if you have long-running malware, that may not be a thing. For exfiltration, after seeing the suspicious DNS query, we started to see traffic flow to 1.2.3.4, which with our reverse DNS table I just talked about, maybe you now know that that is talking to fanciestbear.com. And over time, it ends up sending 250 megs of data to the endpoint, a suspiciously large amount, probably a database or some zipped up documents, something of that sort. And this is an instance that's really important where aggregation matters, because the events that are going to come out of the Microsoft Windows kernel network trace are going to be specifically built around, they're going to be per packet. So you're going to get an event that says, I have 220 bytes sent to this endpoint and to this port. That's going to be problematic if you try to log every single one of those and send that to your SIM. So aggregation is going to be key here, maybe every 15 minutes, maybe every 30 minutes. Build it up, log one event, keep going. Malicious PowerShell, we talked a little bit about this. After bad.exe uploads some data, we see it execute known bad PowerShell function. In particular, let's imagine it's invoke reflective PE injection, which calls create remote thread. Maybe they're going to pivot to a new process for persistence. Nothing new here from the obfuscated PowerShell or the example I showed you earlier. Mainly just that this works for any process that loads system.management.automation. Finally, we see bad.exe inject a thread into another process. This is probably from that PowerShell function I just talked about on the last slide. And again, this is a heuristic detection. Not all thread injections are malicious, and in fact, most are not. But this is a good next step to use to trigger a scan, right? So imagine you have a process that you've just seen get a thread injected to it. You say, okay, well, my agent's running at local system. I'm going to go and open up memory on that particular process, and I'm going to scan memory and I'm going to scan the threads that are running in that process and look for threads that are running in memory that a DLL or an executable is not allocated to. So this will give you a really basic, like, oh, somebody's hollowed this process or done something suspicious there. So what do? We forward everything to the SIM, turn on all 1,100 providers, and just let it go. That'll be fun. Let me know how that goes. It's going to look a lot like that. So I have a black lab at home, and this embodies everything about owning a Labrador Retriever. Just absolutely everything. This is your SIM on unfiltered ETW. So it's event overload, right? The ETW is really meant for debugging. It was never meant to be used the way that we're using it now. It happens that we can, but it was never meant for that. And so, I mean, think about it. Can your SIM handle every image load for every process on every machine across 10,000? Can it handle every single packet sent across your network? How about every DNS resolution by any client in a 10,000 data center server? Probably not, if I were to guess. If you can, I'd love to hear how you're doing it. So let's talk about reducing event volume down a little bit. Take a break here. How do we reduce that? Imagine you have this huge number of raw events that are enabled from all your 15 or 20 providers you've decided to turn on. Well, you have that custom event handler that we talked about a little bit earlier. So you put it all in there, and you do some smart things to reduce the amount of data that you're pumping through there. And you'd like to ingest those events in a sane way that your SIM can actually consume. And so this is super key. This is where the power is, because there's not really a good way to do this with log files. But you can do it with ETW if you're filtering, and especially if you're filtering at the native layer using a custom event handler. Let's talk a little bit about signals for reducing volume. And it's helpful to think about 4 types of signals, in my opinion. This is not the end-all be-all of signals that you get, but it's the way that we kind of think about them in Office 365, and I'd like to hear what other people think and see if I've missed anything. So we have an oracle signal. An oracle is kind of our generalized name for an allow list, deny list filtering solution. Something is able to tell you this signal in the deny list is alertable, or the signal in the allow list, or signal that's not in the allow list is alertable. And so practically speaking, like I said, this is a filter, whether it's a list of domain names that you know are bad, like fanciestbear.com, or even a set of processes that are allowed to load PowerShell's runtime. Or, you can think of any number of these endpoints that are known bad because not Petya or something. Then we've got aggregation. We talked briefly about that. It's a signal that we're just going to take everything and accumulate it together. And this is most commonly used by us in 2 spaces. Number 1 is I talked about, which was networking, right? Every event is a packet sent. So you got to collapse all that down into a useful amount of data. Number 2, if you try to monitor PowerShell on big scripts or on machines that run lots and lots and lots and lots of PowerShell, every single method's coming through there. And now you're doing so every single method being logged to the event log isn't that useful, but maybe you just collapse it down once you get your first hit on a bad thing, right? Maybe you saw invoke Mimikatz. Well, let's just collapse all that down to one event from that process and just log that instead of doing all of them. Then we have our heuristic signals. I kind of alluded to this as well, talking about remote thread injection. And so these are low to medium fidelity signals, and they may indicate that something like a process is worth investigating more thoroughly, but they don't necessarily mean you need to call the on-call engineer, at 2 in the morning. Heuristic signals they're good for triggering analyses, but they're not good for triggering alerts. So again, this is that memory scanning algorithm that we were talking about. And finally, we have statistics. So I talked a little bit about that when we were looking for obfuscated PowerShell method names, where you're talking about Shannon entropy and bigram analysis. You can also imagine looking for a beacon, like a beaconing process. Well, think about using a statistical model to build out whether or not some signal is regular over time. And if you're interested in that, come talk to me. My boss knows of a paper where we can point you at. Many machine learning algorithms are actually ultimately instances of statistic signals. So I didn't leave that out intentionally, but ultimately that's what most machine learning algorithms tend to play down to at implementation. So here's a breakdown of these techniques applied. The malicious PowerShell is using aggregation and an oracle signal. So here's our deny list of function names combined with our aggregation so that we're not spamming. Obfuscated PowerShell, which is using our statistics. And then data exfiltration using aggregation and an oracle. So, for example, with data, when you're monitoring network traffic, you usually want to be whitelisting your VLAN because there's so much data that's going between all of the machines internal to the network. So you're really more interested in watching what's going across the boundary from in to out. And in that case, that's why the oracle is on here. Then you have DNS lookups. Again, that's an oracle. Is it bad? Is it good? Thread injection is a heuristic for taking further action. And of course, PowerShell Loaded is an oracle plus a heuristic because you may not know exactly what's loading PowerShell legitimately. Now, some caveats here. Oracles have a problem, right? If an attacker compromises the oracle, for example, by adding malicious entries into an allow list, you may be blind to that malicious behavior. So, something to think about as you're building out these techniques. Not everything's sunshine and rainbows. Let's talk about some gotchas. These are problems that you may encounter trying to use ETW, and also problems you'll want to monitor for when your red team comes through. For performance and reliability space, CPU usage is directly correlated to event volume. And it's almost always network data. You need to filter out the internal VLAN badly. Events can be dropped if you don't pump fast enough. So the way that ETW is implemented on the API side is actually there's an event buffer, and it's a ring buffer. It defaults to 64K. And ETW just keeps pushing events in there, and once it comes back around, it's just going to start writing over the old events. So a super important concept is returning control of the pumping thread back to ETW. And so when you're processing lots of events, you want to send these off to an async process of some sort, whether that's just another thread whose only job is to process events. Again, filtering is also really important here. And occasionally ETW will write bad or missing data. Once in a while we get a process start where the process image name is mangled. Sometimes we end up with data that is just simply corrupted or missing. On the tampering side, we have trace sessions. They can just be stopped by administrators. There's nothing that stops them. They can also be modified. So imagine your agent has 6 providers turned on, and it processes about 100 events per second. And malicious attacker comes through and says, well, I'm going to turn off your PowerShell provider, I'm going to turn off your network provider. And so now you go from having 100 events per second to having 10 events per second. Well, you didn't lose all of your signal, right? So maybe your agent is still alive, but it's really weird that you lost a subset of your process or a subset of your events, or possibly you might be able to monitor for quas drops. So this is an important problem, and I'd like to see an ACLing solution come around from Windows for this sort of thing. Malicious software can also write fake data or bad data, and that's hard to do, but it is possible. And so the concern there is, I don't think bad data is as concerning, because typically what happens there is if you poorly handle it, you end up crashing the process. That sucks, but that's a thing. I'm more concerned about the red team lying to me, or the attacker lying to me by injecting fake data in there and clouding out signals that might otherwise be meaningful. So what did we find, right? Let's talk a little bit about what we actually saw in our environment using ETW. How does the red team do, right? Well, using ETW, we found them calling WMI. We found them doing PowerShell method execution. We found them loading PowerShell into anomalous processes. We saw new processes uploading into external endpoints, and so that's a combination of beacon and or aggregation signals. The beaconing processes here. Oops. So these are not everything we've ever seen from the red team via ETW, but it's a good high-level value add, in my opinion. These were some of our best detections for catching them. Now this is a fun graph. This is using network data from our ETW combined with what our agents recorded. This is a network graph of what our agents are talking to. And so those gray nodes in the middle, the little circular ones, are processes. And the green nodes are Microsoft properties, whether it's SharePoint.com or OneDrive or something like that. And the teal nodes are Azure properties, and the red nodes are external. So think Akamai, Cloudflare. And the red arcs that you see going between the nodes, those are beacons. So the point here is that a lot of times what you end up finding out as you are building out these improved monitoring solutions is that you don't actually understand your environment as well as you thought you did. You don't know what the shape of it is, right? If you don't have perfect inventory and a perfect understanding of what everything is talking to, you might think, nothing talks to Akamai. Well, it turns out that one service team over there needed to use Akamai for something, and so they put stuff through there, and then all of a sudden you've got beacons coming from Akamai, and you're like, sound the bat phone, or call the bat phone. But unfortunately, without doing something like this, you really don't have an understanding of what that environment looks like. So this has been really helpful for us. And of course, everyone's favorite, will it scale? I get this question relatively often when I talk to people about ETW. So we're running on more than 100,000 machines across our production environment, and we're gathering more than 7 terabytes a day of data, and we're processing more than 500 billion events per day across the environment. And that's after filtering as of January 2017. The number of machines in the environment has almost doubled at this point. So I hope that the issue of scale and how important filtering and is clear, right? We're filtering and we're still having to handle this much data. Now granted, the way that we deal with the data once it's written is we're using a MapReduce system called Cosmos to post-process this and generate better signals out of it. But the difference here is that the signals just from the security event log gave us very poor signals, but these improved signals coming from ETW are giving us real detections that we can act on and actually generate, SEV1s that we can wake up in the night and actually do something about. All right, I'm still talking, which means that I've made it through without fainting, and I've also made it through by almost getting there. I'm 10 minutes early. Cool. But we're not done. Not entirely. So how do you actually use ETW in your environment? Well, number one, krabsetw. I'm going to have a link at the end where you can get to the GitHub repo. That also links to the NuGet packages, the demos, etc. It's open source under MIT license. It's compatible, as I said before, with Windows 7 and Windows 2008 R2 and above. The PowerShell method auditor is a little tool I wrote for Daniel Bohannon to play with. That is specifically, it's a good example of what our real PowerShell detection looks like, minus our deny list for methods, because you can build that out yourself. But it shows this is how we actually are handling and processing these events. Again, I'll have some short links at the end. So what's next? I spent a lot of time talking to a lot of folks today, today and yesterday, and the consistent feedback I keep getting from people is that people want a signature-based tool. And that was not something I was really aware of, because kind of like the hammer that we use at Microsoft is code. Like if you don't know what else to do, maybe write more code to solve the problem, or delete code, which is actually a better thing. So, and to Lee's credit, Lee tried to put this idea in my head 3 or 4 months ago. He sent me a sample of wrapping crabs in PowerShell. And I didn't understand why that was useful, because I was like, who would write an intrusion detection system in PowerShell and run it on machines and expect it to be performant? And so that was just a failing in my part to understand what people outside of Microsoft are doing. And so I'm trying to get better at that. So I'd love to hear how you would like to use ETW. The things we're entertaining right now are the ideas of Sigma or Yara signatures combined with ETW to pull those events out. And I want to note prior art here. ProcFilter, which is a project released by GoDaddy, actually does this. They have Yara filters for ETW. So go check that out. I think it's just GoDaddy/ProcFilter on GitHub. And then there's flat C APIs. So this is something I heard from a couple of folks who actually do work on agents and write code. One problem we have today is our C++ library is very modern C++, which is not easy to interface with for people who are using languages like Go or Python. And so a flat C API is a lot easier for people to use. And so if people are interested in that, I have a basic prototype of how to do this. I just need a little convincing that it needs to be built. I'm pretty sure it does. And like I said, these don't really exist yet, but I'd love your feedback. So, time for questions. Those links are all of the useful pieces of information that you might want from this talk, in my opinion. /ETW is going to be the link to the krabsetw repo. /ETW demo is the demo code for everything I showed here. In addition to the demos I showed for example code, I also have a basic exfiltration example. And then PowerShell method auditor is also available on GitHub. And then finally, that's the message analyzer link. Thank you. So the question was whether or not I'm aware of ETW tampering in the wild by a malicious actor. I don't know. Do you know, Matt? We see research on Defender ATP, which uses ETW. But I'm not personally aware of any for our agent. But I'm sure it's coming. Cytoscape was what was used for the graph that we showed for the network connections. How frequently do we stop and restart the trace? Ideally, never. I can only speculate. So let me put it this way. Mandiant released a tool called PyWin Trace that can consume ETW. So internally to Microsoft, not as far as I'm aware, but that I wouldn't be surprised if the Defender ATP team was doing it. Some sandboxes internally, possibly, but I'm not sure outside the company. So ETW is actually built into every component within the operating system. It's already there. It just has to be turned on. So the way that we do it is by using code. In the example code, when I was turning on subscribers, that's all we're doing to turn them on. And then when we process the events, we write them to the event log. But that's all we're doing. We're not using any GPOs for anything. So we probably wouldn't release anything to help push it to a centralized management. Probably, I think the Windows way to do it is wecwef. If you write the events to the event log, the solution as far as writing them out, I didn't cover it, but the way we're doing it is writing event logs. I've heard of other teams writing JSON or XML files out. Like I said, I'm still learning on this point, and so I've realized that what people want are tools and signatures, not necessarily libraries to go build their own agent. Some people want that, some people want the tools. So we're taking that feedback, and we're going to try to help make that easier for folks. Pardon? So the question was whether or not stack trace capture is enabled on the ETW trace, and right now it is not. I've had 2 people ask me that since I told them about it at Derby, and I have a request on GitHub to do it. So it's actually planned for this upcoming quarter to go and enable people to add whatever options they want when recording ETW. We don't actually use it because it's too high volume for us, but I can imagine why that's useful for others. Any other questions? No? Cool. I'll get out of your hair.